worry. We've just got a couple of lectures left, I think, on the material before we can then start to move into thinking about revision and preparation for the examination and so on. So just to recall where we are, we're talking about groups. Groups. A group is an algebraic system, a mathematical algebraic system consisting of a set and a single operation on it. Okay? We discussed this definition quite a few lectures ago, 2 or 3 lectures ago. So it's a set together with a binary operation, a way for taking ordered pairs of elements from the set, combining them in some way. Think of things like addition of numbers, multiplication of matrices, that kind of a mathematical operation between 2 elements to give you another element of the same sort in the same set G. If it satisfies these basic algebraic properties here in statements 1 to 4, then it's called a group. Okay? And groups are a very natural mathematical structure to look at. A set of things and an operation on them. Various sets of numbers, and the familiar operations of addition, multiplication, and then other kinds of operations as well. Sets of functions and the fundamental operation of composition of functions, combining different processes one after the other. Sets of matrices under addition or multiplication of matrices and so on. So it's a very common structure or pattern to see in mathematics. And so group theory studies the possibilities that can satisfy these basic 4 properties. It turns out to be a very, very rich and complicated structure of the kind of universe of possible groups. And we're only kind of touching on a few of them here in this kind of introductory material on groups. Now, I'm going to pick up from where we were last time, where we're looking at permutation groups, or groups of objects called permutations. So permutation groups are groups, sets, where the objects inside them are called permutations. What's a permutation? A permutation is, well, some way of rearranging n objects. Permutation on n objects is some way of rearranging them, reassigning them to each other in a bijective way. So each object gets associated to another object in the same set of n objects, and it isn't the case that 2 objects get sent to the same object. So it's injective. Now, it is customary and usual to use the labels 1 to n for the objects. You could easily well use the letters A, B, C, D, E up to whatever the last object is. The only role these numbers are going to play is just as labels of the objects. We're not going to be taking any use of the numerical nature of the labels. They're just labels for n different things. And so for each of the, so the objects are permutations, which are functions from the set of n labels to the set, to the same set, to the set of n labels. It's a rearrangement of them. So, and the operation we're talking about is composition of the functions. So for any given value of n, any given number of variables, you've got a group. And it's called Sn, and it has the name, it's called the symmetric group on n objects. We talked last time, we discovered if you count how many different possible permutations you can construct, you get the answer n factorial. So we completely understand what the size of this group is. And as n gets large, n factorial gets very, very large for sure. Okay? So when you got a lot of objects, there's a lot of different permutations amongst them. Yeah? So how do we deal with these permutations? How do we describe them or do calculations with them? Well, the first way we introduced was the 2-line notation. So here's a particular permutation sigma. It's got this 2-line symbol, this kind of matrix-like symbol. So matrix-like symbol. And what that stands for is the function defined by these values down here. Sigma of 1 is 2, sigma of 2 is 4, sigma of 3 is 1, and sigma of 4 is 3. Give the arguments to the permutation on the top line and the corresponding values that they take under the function sigma on the bottom line. And we looked at various ways we can use that in composing it and so on. But it's a little bit wasteful, this notation. I mean, if we're always going to write, if we're looking at permutations on 4 objects, if we're always going to write the numbers 1, 2, 3, 4 across the top, it's a little bit wasteful and repetitive. We don't need to do that. And moreover, it's not immediately obvious what some of the finer structures, what some of the inner structure of the permutation is from the 2-line notation. Whereas, for any permutation, it does have a natural inner structure. Remember, we looked at the example where any given permutation, you can look at it and you'll see that it naturally decomposes into a number of disjoint cycles. When you look at where the elements get sent, you notice that for any permutation, there'll be some kind of subset of the labels, maybe all of them, but some kind of subset of the labels that just get cyclically permuted. Each one gets sent to the next one. So you put them in some kind of cyclic order. And that gives rise to the cycle notation. So this is a different type of notation for a permutation. So here's a different sigma. This 1-line notation, 13524. Which permutation is that? The way the notation works is this stands for the permutation defined by these values. It sends the object 1 to 3. It sends the object 3 to 5, the object 5 to 2, sends 2 to 4, and the last label that appears in the notation, number 4 here, it gets sent to the first one in the list. Okay, so they get cyclically permuted. They get moved on one position in the cycle of labels. The last one gets sent to the first one. Now, there's also a convention that with this sigma, now you see up in the first line it says sigma. This sigma is an element of S8. So it's a permutation on 8 objects. But of course, in the notation, it only mentions 5 of them. 1, 3, 5, 2, and 4. So what does sigma do to the other objects? The objects labeled 6, 7, and 8. Well, because they're not mentioned in the cycle notation, it's understood that this sigma leaves those objects fixed. It sends 6 to itself, it sends 7 to itself, and it sends 8 to itself. So then we did some example, and I'll just do another one of these examples now before we continue, just to kind of reconnect with it a bit. So given any product of cycles, I'll just make up an example. So here we are working with cycles. Here's another example. Consider the following. Consider the permutation sigma. Let's say it's an element of S10, a symmetric group on 10 objects. Suppose sigma is presented to us as the following composition of cycles. Now I'm going to give it as a product of cycles, but they won't be disjoint. Suppose the first cycle is 1, 8, 6. The next one is 3, 1, 5, 2, 8. And this one here might be 7, 6, 3. So there's sigma presented as a product of cycles. When I say the word product, in this context, this group S10, the group operation is composition of the functions. That's what I'm meaning when I say product. So it's a composition of functions, so remember, by convention, when you write down a composition of functions, the usual convention, and the one we're going to use in this course, and we use in most courses, is that the first function that's applied is the one on the right. It's a right-to-left notation. The second function that's applied is the one in the middle, and the last function that's applied is the one on the end, on the left. Now, in order to fully appreciate the kind of inner structure of sigma, to really see what sigma is doing, we'd like to see its representation as a product of disjoint cycles. So we seek the more informative representation of sigma as a product of disjoint cycles. Any questions so far? Any questions on this problem that I've set up? Is it on any of the definitions involved or any of the terms? Anything you'd like to clarify before we continue? See, it's not immediately obvious from the way sigma is presented there. It's not immediately obvious what the disjoint cycles in sigma are. So let's work them out. Now remember, these labels, okay, I've only mentioned some of the 10 labels there. They're just labels for a collection of different objects. There's no first object, second object, third, they're just distinct labels. So let's just start. Let's start 5. Just choose an arbitrary starting point. So you see, one of the cycles in the disjoint cycle representation of sigma, one of them will have a 5 in it. What we're going to just start to do is start to examine it and see what the rest of the cycle containing 5 is like. So we're asking ourselves, what comes after 5? Well, we just apply sigma to 5 and see what happens. This is the first cycle, this is the first permutation that's applied here. What does this one do to 5? Nothing. It leaves 5 fixed, sends 5 to itself. So 5 is the intermediate value, which gets passed on to the second function. Now this one does do something to 5. It sends 5 to 2. So 2 is the intermediate value. Remember, the output from this function has to be fed in as the input to the last function. So we have an intermediate value of 2, which passes on to this one here, but that one leaves 2 fixed, because 2 isn't mentioned. So overall, when you apply sigma to 5, you get out the value 2. You get the value of sigma evaluated at 5 is 2. So whatever this disjoint cycle is, the beginning of it, if you start at 5, it begins 5, 2. So you just seek to continue it. What happens to 2? And we might speed up a little bit. The first one leaves 2 fixed, so 2 is again the intermediate value. The second one sends 2 to 8, so 8 is the intermediate value. The last one sends 8 to 6, so 6 is the final value of sigma applied to 2. So 6 is the next element. Is everybody okay on how I'm obtaining these values then? Any questions at all you'd like me to clarify? Okay. So we keep going. What happens to 6? 6 goes to 3, 3 goes to 1, 1 goes to 8. Overall, 6 goes to 8. And what happens to 8? It's left fixed. 8 goes to 3, and 3 is left fixed, so 3 is here. What happens to 3? 3 goes to 7. 7 has remained fixed, and 7 has remained fixed. I think I might just have one giant cycle here. What happens to 7? 7 goes to 6. 6 is left fixed. 6 goes to 1. What happens to 1? 1 is left fixed. 1 goes to 5. 5 is left fixed. So overall, 1 goes to 5. So I'm tempted to write down a 5 here, but no, I suddenly notice 5 is the first element of the cycle. So 1 gets sent to 5. So this is the closure of this cycle. I didn't want it to end. I was a bit unlucky. I wanted to get a few different disjoint cycles, but you see, we've actually mentioned all the labels here. All the labels Isn't that true? All the labels that were mentioned up here have been mentioned down here. Now we could, so sigma really is just a single cycle. Now that wasn't obvious at all. I didn't know that from looking at the first representation of sigma, the product of these ones, but it becomes apparent. So now, with having done that calculation, I understand sigma a lot better. Okay? It just consists of these 7 objects, and they're arranged in this cyclic order. And what sigma does is it just sends each object on to the next one in the list. And the last one, it sends back to the first one. Okay. Why did I choose to start at 5? That was just completely arbitrary choice. I could have chosen to start at any of the other labels mentioned, and I would have obtained the same labels in the same cyclic order. Okay? So equally well, we can write this starting at any point. So you could easily write this as 8, 3, 7, 1, 5, 2, 6. It refers to the same function, just a different symbol. It's a different string of characters, but it represents the same function. Okay? So it's the same labels in the same cyclic order. Okay. Any further questions on that? Yes?
You said sigma is x10, and you've only got 7.
Yeah.
So what happens to the remaining 3?
What happens to the remaining 2? So we can see from this notation what sigma does to these labels. What does sigma do to, so which ones have I skipped out? 9, 10, and 4, isn't it? So so if I need to know sigma completely, I need to know what it does on these. But remember, the convention is that if a cycle does not mention a label, it leaves it fixed. So sigma of 9 is 9, sigma of 10 is 10, and sigma of 4 is 4. So those are referred to as trivial cycles, or one cycle, cycles of length 1. So you could picture sigma here. Just throw the n objects down on the table. You can see what cycle we're talking about. You can get a visual representation of it. 2 goes to 6. 6 goes to 8. 8 goes to 3. 3 goes to 7. 7 goes to 1. So that's the single closed cycle. These elements are sent around in this cyclic order, and these 3 elements are these trivial one cycles, cycles of length 1. One thing I maybe didn't address specifically. What is sigma inverse? Can we write, is there an easy way to write down some description of sigma inverse?
You just say you go from left to right.
Sorry?
You go from right to left.
Yeah, so it's
left to right.
the same string of symbols, same string of labels, but written down in the opposite cyclic order. Because remember, what's this inverse element? The operation is composition, so we're talking about the inverse function. Well, if sigma is the function that sends all these elements this way, the inverse function is just the one that sends them all back. You just reverse the direction of all the arrows. In terms of the cycle symbol, the cycle notation, that's the same as saying you just write them down in the opposite order. So sigma inverse, again, I'll choose to start anywhere. Let's start at 7. So it's 7, 3, 8, 6, 2, 5, 1. So that's the cycle notation for sigma inverse. Or working from the initial description of sigma, I could say sigma inverse is that still on the screen up there? Yeah, just wait. Yeah, so what about that initial description of sigma as a product of those non-disjoint cycles up there? How would we describe, working from that, how would we describe sigma inverse? It's using this idea that the inverse of an individual cycle is just the same labels written down in the opposite order, but which is the first cycle I write down here?
So the one on the right.
Yeah, it's the inverse of the one on the right. So it's 673. Now the inverse of the one in the middle, 1, 3, 8, 2, 5. And lastly, the inverse of the one here, 6, 8, 1. Yeah, because remember, when you're talking about functions, the inverse of a composition of functions is the composition of the individual inverses, but right in the opposite order. Okay? Same phenomenon as when in the morning you put your clothes on in a certain order, in the evening before you go to bed, you take them off again, but in the opposite order. So, I put on my jacket last, I have to take off my jacket first. It's just a natural aspect of reality. To undo a sequence of operations, you undo them, you undo each of the individual operations, but you have to start with the last one you performed. Right. So that is disjoint cycles and inverses. Now, another terminology or another concept, another important concept for permutations we also emphasize the role of transpositions. When working with permutations. Now, what's a transposition? I happen to find that for you. A transposition is a two-cycle, cycle of length 2. Some pair of labels x1, x2, it's just a 2-cycle. Okay? You get your 2 labels x1 and x2. It's the permutation that sends x1 to x2, x2 to x1, and it leaves everything else fixed. Any other labels that are knocking around get sent to themselves by this permutation. Okay? It's a 2-cycle. And 2 cycles are a useful kind of technical tool to have to talk about permutations for the following reason. Why are they a natural thing? Well, there's 4 objects, right? If I want to cyclically permute 4 objects, let's say I want to cyclically permute them up the screen. So each one I send to the position of the one ahead of it. And the keys go back to the first. Okay? I've cyclically permuted them. However, another way to achieve the same result of cyclically permuting a list of objects is to perform a sequence of transpositions. You start with the last 2 objects and you transpose those. Then you step backwards, you look at the next pair and you transpose those. You keep repeating that. Step back and look at the next pair. I transpose those. What I just did there by applying that sequence of transpositions, swapping pairs of labels, starting at one end of the list and working my way down to the other end, I've carried out that same cyclic permutation. So what transpositions allow you to do is to get kind of another nice, kind of almost unique, or another kind of informative representation of permutations. So this is, I think it's listed as a, is it even listed as a theorem? Yeah, it's listed as theorem 5.7 on page 68. 6.5.7, maybe 5. Theorem is a bit of a grand term for it, for what it is, but any permutation can be expressed as a sequence of permutations, as a composition of permutations. Composition, sorry, I keep saying the wrong word, of transpositions. That's the... Any permutation, if we so desire it, can be broken down into a product composition of a collection of transpositions. It's not, I still think, thinking of a permutation as its representation of a product of disjoint cycles, I think that's the most natural way to think of a permutation. But for reasons of computation, for finding these things on a computer, or for other ways of approaching permutations, it's also useful sometimes to be able to think of them broken down into very minimal structures. And the most minimal, non-trivial permutation you can have is a two-cycle, a transposition, where you just swap positions, 2 elements, and you leave everything else fixed. Now, this really, okay, I say theorem is a bit of a grand word for it. It doesn't really require a huge amount of proof. So working from a permutation expressed as a product of cycles, okay, and that's typically how we encounter permutations. They'll be expressed as some combination of cycles, not necessarily disjoint. Each cycle can be decomposed as, now, here's there's an attempt to represent a general cycle. Collection of n labels, and here they are, the first label A1, the second label A2, the third label A3, and so on. There they are. And really, well, what I'm going to write down now here is really the same thing I was demonstrating with my pens and my keys. So we start off by swapping the pair AM-1 and AM. You swap the last pair. You then step one back and you swap the third to last and the second to last, AM-2, AM-1. You just keep working your way back through the list. And the last two that you apply are A2, A3, and then the final transposition is A1, A2. So any cyclic permutation, which is what we got on the left, can be realized, can be expressed as a sequence of transpositions, sequence of flips, where you're just flipping a pair of labels and leaving everything else fixed. And you start from the end of the list, flip the last two on the list, and step back, flip the next last two. Keep doing that until you work your way to the start of the list. So let's do one of these examples. Try example 1 there, 5.10. So this is to just express the following permutations from S5 as a product of transpositions. Okay, there's a permutation. First of all, we'd maybe seek the expression for it as a product of disjoint cycles. So starting from 1, 1 goes to 3, 3 goes to 5, 5 goes back to 1, so it has a 3 cycle in it. And 2 goes to 4, 4 goes to 2. So that's the representation of it as a product of disjoint cycles. Now actually 2, 4 is already a transposition, so we can leave that. But then the 3 cycle breaks down as the product of transpositions 3, 5, and 1, 3. Okay, so you're seeing there lots of different ways of representing the same permutation. The original kind of least informative way, which is the 2-line notation, just simply lists all the values of the function on all its possible arguments. The most direct but the least informative way of representing. The middle way, as a product of disjoint cycles, that's the most kind of informative way, I think, the most structural way. Tells you this permutation has within it 1 3 cycle and 1 2 cycle. And then the final way is to represent it as a product of transpositions, okay, breaking it down into smallest possible bits. The smallest possible non-trivial bit in this context is transposition, flip of 2 elements. So I'll just switch back to the notes for a moment. Now this is kind of looking ahead to, some other things, or some aspects of, what are the next kind of topics in group theory, or what kind of things does group theory go on to? Well, there's a theorem. When you break down a permutation into a product of transpositions, minimal 2 cycles, you see there's lots of different ways to, break it down. Because the same permutation can be represented as a product of cycles in many different ways when the cycles are non-disjoint, you can generate many different representations for the same permutation as products of transpositions. However, what will be the same is, for any given permutation, there will either be an odd number of transpositions in its representation or an even number. So for any given permutation, it will be possible to represent it as a product of a different number of transpositions, but the parity of that number, the odd or evenness of that number, is always the same. So any given permutation, it either has an odd number of transpositions in it, or an even number. Okay? And when you gather together all of the even permutations, you get a subgroup of the symmetric. And it's a subgroup, it's exactly half the size of the whole group, Sn. So if you collect together all those permutations which are even, and they're even in the sense that in any representation for them as a product of transpositions, they always have an even number of transpositions, then they form a kind of, the most important subgroup, or, a prominent subgroup of Sn called the alternating group. This is the largest subgroup of Sn that isn't all of Sn itself. Okay. Remember, just as when you're studying vector spaces, just as a vector space can have subspaces within it, subsets of the larger vector space which act and operate as little vector spaces all by themselves with respect to the addition and the scalar multiplication, in the same way, when you have a group, you can have subgroups within it. Little subsets of the large set which act like little groups all by their own with respect to the same operation that's going on in the large group. Now, in the end of chapter exercises, you'll find a whole bunch of things to do. I've mainly concentrated on permutations. Also down there in question 10, you see, okay, I haven't addressed this point exactly. I'm leaving you to figure this out and puzzle this out. So you see those two equations in question 10. They're equations amongst permutations. The permutations are represented as products of cycles. But you've got an unknown, in the first one there's an unknown permutation sigma on the left there. The second one there's an unknown permutation tau in the middle. So you're asked to solve those equations. Now, I'll leave that with you. That's something to consider in the tutorials. Or I'll address it, maybe we can do some examples like that in the next lecture. I'll be taking you for the lecture tomorrow, won't I? Yeah, it's an odd week. It's week 9, yeah. So we'll do some more examples with these and exercises with these tomorrow. Some more complicated questions, or some more deeper kind of question. Question 12, are any of the symmetric groups abelian? What's an abelian group? Remember, an abelian group is where the operation on the group is always commutative. So in products, in the group, you can always change the order of the pair of elements and you get the same answer. So ask yourself, are any of these groups Sn abelian? Now this section, going further here, this really is kind of a look ahead at an important result. It's an important early result in group theory. So if you end up doing the third year group theory course, taught by myself and, well, taught by myself at least, we invest, that's a full course, full introductory course on group theory where we really get to grips with studying the mathematical structure of groups. But here's a very important early result that we get to, and it'll have a prominent place in that group theory course, and this is Lagrange's theorem. Lagrange's theorem deals with finite groups. Most of the examples of groups I've shown you have been finite. The dihedral symmetry group, D3, the group of symmetries of a triangle, I showed you first. The modular arithmetic groups, they're all finite groups. These permutation groups, they're finite. In any group, there's only a finite number of objects in it. Lagrange's theorem is a very informative theorem. What it does is it places restrictions on the sizes, on the possible sizes of subgroups of the large group. And it's a very classical kind of abstract algebra, abstract group theory result in that it's saying something about every possible group. Okay? It's not a specific statement about permutations. It's not a specific statement about modular arithmetic. It is a statement about those two things, but not only. It's a statement about every single group, every possible algebraic system which satisfies the group axioms. And it's really nice, really simple to state, and it kind of links into number theory in a way, because it's talking about factors of numbers and stuff, which is what we study in number theory. So it basically says that when you've got a finite group, the only numbers you see as sizes of the subgroups are numbers that divide the order of the containing. So if your containing group has order 10, if your containing group is size 10 elements in it, the only possible sizes of subgroups that might arise, that you might see, are groups of order 1, 2, 5, and 10 itself. Because the numbers 1, 2, 5, and 10 are the only numbers that, the only integers that evenly divide into 10. If we encounter a group of size 10, we automatically know it cannot have within it a subgroup of size 3, 6, 7, 8, 9. They just cannot arise. Okay? We automatically know that from Lagrange's theorem. Okay? So Lagrange's theorem will be one of the first kind of substantial results that we prove in the third year group theory course, and it's quite a nice result. Okay? And it definitely gives a flavor of, you know, the kinds of results that abstract algebra group theory is after and seeking to prove. So as a way of observing, I never bothered to capture my screen work today. Sorry about that. Anyway, yeah, let's just go here. As a way of confirming Lagrange's theorem in one particular case, let's look at our old friend. So this is our old friend D3, the group of symmetries of the regular triangle. Remember, this was a group with 6 elements in it. The identity element, leaving the triangle alone. 2 non-trivial rotations, rotating by 1/3 of a full turn, rotating by 2/3 of a full turn. And there are 3 reflectional symmetries. You can reflect in any of these 3 axes. The axes go through a vertex and the midpoint to the opposite side. These are the 6 objects in the group D3. This was its multiplication table, the Cayley table for the group. Now, just as a quick, rough and ready kind of way of thinking about it, what are we doing when we're looking for subgroups of D3? We're looking for subsets of D3 which are closed with respect to the operation. Now remember, the size of D3, the number of elements in it is 6. What possible subgroups does it have? Well, it has the trivial subgroup. The trivial subgroup is always around. This is the group just consisting of the identity. The most boring group in the mathematical universe. There's just one thing in it, and when you multiply it by itself, you get the same thing. E times E is zero structure to appreciate or investigate, apart from the fact that it has one thing in it. Slightly less boring, still pretty boring, are the subgroups formed by a single one of the reflections. So if you have one of the reflections, S1 say, reflecting the plane in an axis, when you do it twice, you get the identity. S1 composed with S1 is the identity. So you've obviously got the other groups like that, ES2 and ES3. There's only one other subgroup. What's the other subgroup that D3 has? There's two. Well, sorry. Any in a kind of trivial way, the whole group qualifies as a subgroup of itself. The whole thing is a subset of itself, but it's not really a proper subgroup. So, okay, D3 is a subgroup of itself, but what's the only other proper subgroup that I haven't listed yet? Sorry? What are the elements in it? It has to have the identity, and what are the other elements? Now we know by Lagrange's theorem it has to, well, we're trying to confirm Lagrange's theorem here, but if we sneakily glance at Lagrange's theorem, we know it can only have size 1, 2, 3, or 6. Those are the only divisors of 6 that there are. There's a natural looking subgroup of 3 elements within group D3. I think you mentioned it, but you hesitating on it. You mentioned R. The R, yeah. It's the group consisting of all the rotations. See, we've had the groups consisting of all, the identity in one particular reflection. But actually, if you throw all the rotations in there, that acts as a subgroup. Because what do you get when you compose 2 rotations? When you apply 2 different rotations after each other, they're both rotations of the plane about the origin. Well, you get another kind of rotation, don't you? You rotate the plane a bit, then rotate it another bit. Overall, you've rotated it through the sum of the 2 angles. So a rotation composed with a rotation is a rotation. So if we put in all the rotational symmetries of the triangle there, they form a subgroup. And you can see that in the table. If you look at this bottom right-hand side, if you look at the top left-hand quarter of the Cayley table, this here is the Cayley table of the subgroup of rotations. ER, R squared, all the possible combinations just give you other ones of those elements. So that's a subgroup of D3. So this here, this confirms Lagrange's theorem in the case of D3. Well, strictly speaking, we'd have to examine all other possible combinations of elements within D3 and show that they don't form subgroups. But these are the only closed systems within D3. These are the only closed subgroups. And we see they're either of size 1, 2, 3, or 6, which are the only divisors of 6. Okay, tomorrow's lecture is a kind of worked examples class. I'll do a lot more examples of calculations and problem solving with these. And I'll see you then. So don't forget the font this evening.